All right, thanks. So the topic of my thesis is data-driven modeling, control, and tools for cyber-physical energy systems. And today I'm going to first provide the necessary background and introduce concepts of price volatility and demand response, which will lay the foundation for me to describe the exact problem and my research goals, which I aim to answer in my thesis. I will then talk about the proposed solution approaches to solve those problems and conclude the talk with an overview of my current and future thesis plan. So let's get right to it. The way we consume and generate electricity is gradually changing. So there's a lot of regulation and emphasis on going green and integrating more and more renewables onto the grid, which itself is becoming more smarter and generates more data now more than ever. And there's an increasing thrust on making buildings more automated and responsive to the conditions on the grid itself. So as a result of some of these changes, the grid itself is becoming more and more volatile. So consider this case where as the penetration of renewable sources on the grid increases, it leads to variability in the generation sides, which introduces this volatility in the generation. And this volatility reveals itself partially in form of the fluctuations in electricity price itself. So here's a plot from last year where you can see the price of electricity fluctuates a lot during just the span of a single day. And this is caused because this variable supply can lead to a mismatch between the electricity being generated and the demand at a given time. But variable generation alone is not fully responsible for these steep increases in the prices. The price of electricity also changes when there are peaks on the demand side. And we have a fairly well understanding that on an extremely hot or a cold day due to weather conditions or just human temporal correlation of human behavior, these peaks can occur on the grid. So let's look at another instance of how does that affect the price of electricity. This is just data from a month ago of the US Northeastern grid, where the price increased from $25 in the morning to more than $800 in the late afternoon when the temperatures increased. It would be naive to just think that the peaks occur only on hot days. Here's another example from last year when there was a polar vortex in the eastern grid. In this case, there was an increase of 86-fold in the price of electricity, and the prices increased to more than $2,600 per megawatt hour from just $30 as a nominal rate. And the reason why these prices increased by these huge orders of magnitude is because when peaks occur on the grid, the suppliers or the generators have to rely on more inefficient and expensive sources of meeting that deficit between the supply and demand, which are called these peaker plants. But an alternative to using this dirty and expensive energy is what is called demand response, which is much more cleaner and cost-effective way of mitigating peaks and not relying on this heavily carbon emission plants. And the idea behind DR is the following, that as the generator experiences the load increase on the grid, he anticipates that there's going to be a peak in the near future. So at this point in time, the utilities and the generators dispatch a DR request or demand response request to the end users or the consumers of electricity, asking them to figure out ways to shed their non-essential electrical load. And as a result of their participation, the peak is avoided and it results in a curtailed response. And the utilities then reward the end users for their participation in helping to maintain grid reliability and avoiding the peak. And this is what a DR event notification looks like. It essentially conveys two pieces of information. How much curtailment do we need and what is the time between which we want you to curtail your electricity demand. In fact, if we go back to the Northeastern grid, which is one of the largest in the world, what we find is that demand response, the capacity that it can account for, which is this virtual generation, exceeds that of renewables, combining both wind and solar. And this trend is likely to continue because as renewables are integrated into the grid, we experience these volatile changes. So now that we understand these two concepts, let's hone in on what problem do I want to solve exactly. So the biggest risk which this volatility in prices poses to are the large consumers, end users of electricity, which are these commercial, industrial, and institutional buildings. And in order to shield themselves for this, from this exposure to volatile prices, what they need is more flexibility in the way they consume electricity. So they need to be more flexible in their electricity demand. And the reason why we focus on buildings alone is because They account for a significant share of carbon emission and global energy use, and specifically, they account for more than 70% of electricity use in the United States. Within buildings, if we take a deeper look at what's going on in these commercial, institutional, and industrial buildings, we find that in buildings, the majority of both electricity use and natural gas use is attributed to the heating, ventilation, and air conditioning or HVAC systems. And it is because of this reason why there's a big opportunity of improving the operation of these HVAC systems, which provide the biggest bang for buck in terms of introducing the demand flexibility that we require. So that was partly the reason which led to exploring the area of model-based control for building design as an alternate to traditional rule-based control. So traditionally, buildings were set up in the ways in which they followed a sequence of operations which were predetermined by a building's energy manager based on historical data or the experience of the building itself. A sequence something like this, in which the rule says that at 4 in the morning you start one of the chillers, and as soon as the chiller reaches 90% load, you bring on another chiller online. The shortcoming of such a rule is that it's purely reactive, and it does not take into account all the other conditions which can affect the operation of the building and its aggregate load. So who's to say that yesterday it might only have taken about 20 minutes for the chiller to reach 90% load, and then another chiller came online, but because of changes in weather condition and building operation today, it might take longer for the same effect to occur. But what if the price of electricity increases during that period? Such rules do not account for that. And that's really their main limitation, that they can only account for a limited set of complexity of the scenarios that you can think of. So that's why an alternative to this rule-based control is model-based control, in which we want to learn models of how the building would respond to changes rather than just come up with these fixed rules. And once we have these models, instead of being reactive, they are predictive models and then allow us to design controllers which can optimally trade off energy efficiency and demand flexibility against thermal comfort. And the most popular method of doing model-based control, which has been explored in this area, is what is called model predictive control, or MPC. And MPC really came out of the process industry in the 1980s. And since then, it has found its place in different application areas, including large amounts of efforts to apply them to buildings for the problems that I've described. And the idea behind MPC is that once you have a predictive model of a plant, what you would do is you would use that prediction to figure out the optimal sequence of inputs into the plant, which could be a building in this case or something else. And then you would only use the first computed input signal and inject it to the plant and repeat this process at every time step. So in the context of buildings, our control problem is that we want to figure out the set point or the operating conditions for the heating, cooling, and ventilation systems of these buildings. So if we have a model which relates this to the energy consumption of the building, we could use that to do model-based design. But when you talk of model-based design, the biggest thing that it relies on is how are you getting these models to begin with, and how accurately can they describe the operation of the building. So broadly speaking, the models for buildings are learned in 3 different ways: white box, gray box, and black box modeling. In white box, the way you build a model is you take a real building, and the first thing you want to do is get as much information as possible about the building layout, floor plans, HVAC equipment layouts, and things of a similar nature. And then you want to hire domain experts whose sole job is to look at all this data, parse it in a manner so that he can make sense of this distributed data. And his job is to tune the parameters of a high fidelity building energy simulation model, something like Energy Plus or Transys. So this is a very tedious process. The person has to go floor by floor, zone by zone, wall by wall, even at layer by layer inside the wall, figuring out what are the thermal parameters of conductivity and capacity, and then tries to set up this whole building simulation model, also accounting for the geometry of the building itself. In reality, however, not all information is completely available, and a lot of guesswork and domain expertise comes into play of guessing these values of thousands of parameters required to set up these buildings. And you would think that after going through such a painful process, things will look good, but this is just half the story, because the last and another tedious step is to match the simulated output of this white box model against real data from the building. which will require you to get that data in the first place and add additional sensors, measurement sensors, retrofit the building with more measuring points so that you have a rich enough data set that will allow you to tune the parameters of this model. So the obvious downside of such an approach is that it's very cost and time prohibitive to learn such models, and they're not that suitable for model-based control due to their complexity and scalability issues. They have thousands of parameters and states. So we turn to gray box models and hope that they can alleviate some of the problems faced by white box. And in gray box modeling, everything else is the same except there are two key differences. The first is that we won't model the building in a very fine detail. So we have some level of abstraction in which we want to model the building, but still the domain expert, instead of tuning parameters of a building simulation software, has to set up a mathematical structural model of the building itself, still relying on first principles of physics, and then tune the parameters or learn the parameters of this mathematical model from real data from the building. So broadly speaking, the way this would work is that for a given zone, and every room in the building, you would first account for the different thermal disturbances that can affect the temperature and the electricity consumption of that zone. And for different surfaces, you will use thermodynamical equations and model each surface as a different branch of that RC network, where the R and the C coefficients are, again, the thermal coefficients rather than the electrical coefficients. And once you do this for all the zones across the building, you can lump all of the equations together in a more better representation, like some state space form, in which the states of this model are the nodes of your RC network and describe their evolution, whereas the inputs to this model are a combination of disturbances and your control input itself. And finally, given data from the real building, you would want to use some kind of nonlinear parameter estimation algorithm to figure out what are the values of the R and C coefficients to begin with. So surely that gray box modeling is suitable for control, but it is still very cost and time prohibitive to learn these models because you're not getting rid of the need for adding more sensors and hiring domain experts. And you don't have to take my word for it when I tell you it's cost and time prohibitive. We can look at one of the seminal studies which was done in this area, which came out of the OptiControl project at ETH. And they spent about 8 years and they did it all. They learned Energy Plus models, RC models for their buildings, developed MPC controllers, added sensors, got data for a real building itself. And at the end of that, their big conclusion in one of the reports published earlier this year was that the biggest hurdle in making any model-based control being widely adopted in the market is the cost and effort required to train these models or obtain these models. And all these problems are further compounded when you think of the fact that each building is designed uniquely. And unlike the automobile or the aircraft industry, they don't follow a single design. So you have to model each building uniquely. The lifespan of these buildings are also really long, and their operation can change, they can be renovated, and then you have to repeat the entire process again. Finally, buildings itself are these messy cyber-physical complex systems in which these hundreds of systems interact in nonlinear ways it's difficult to account for because they are closely coupled, and you cannot find models which accurately reflect reality while being suitable for control as well. So we turn to black box models, in which the idea is that we will just rely on data and not care about physics-based principles to learn a predictive model for the energy consumption of the building. And this has been done, this approach has been taken and looked at quite in detail, partly also because it alleviates some of the domain expertise and this process could be automated. However, the downside of using just any black box model is that it's still not suitable for control synthesis. Although these models are really good at predicting aggregate power consumption, like something like a neural network, it is still not very suitable for figuring out the operating conditions of the HVAC systems. And usually they are used for coarse-grain predictions for the building energy consumption. So if we want to look at how modeling difficulty relates to suitability of a model for control, what we can find is that white box models certainly lie on the right side of this plot because they are very unsuitable for control and cost a fortune to learn and a lot of time as well. Gray box models are suitable for control, but still it's very expensive to learn these models to begin with. And finally, black box models, although are low cost, they are largely unsuitable for traditional model-based design approaches. So in my opinion, the way we can fix these problems is twofold. Either we have to think of some techniques to lower the cost of gray box models, or we have to make black box modeling more suitable for control and be able to do closed loop control with. And these two problems are exactly the goals of my research. So I want to come up with methods that allow you to do cost-benefit analysis for gray box models and figure out what's the anticipated sensor cost that you require to learn these models. And hopefully that analysis will lead you to make decisions about whether or not you need some particular sensor or not. But more importantly, I want to develop and evaluate data-driven models which are control-oriented and can be used to address the problems of demand flexibility and be applied to something as real as demand response. So now that we understand what my goals are, I'm going to walk you through the two approaches that I have taken to answer each of these goals. So we know now that any advanced algorithm will require a very model of very high accuracy, which in turn requires you to have a lot of data and a lot of measurements from the building in order to tune that model. So the first thing we want to analyze is really how does the quality of sensor data affect the model accuracy that you learn from that data. And sensor data can vary due to many reasons. One of them being that the sensor placement and density can affect the measurement quality of the thing that you're trying to measure using the sensor. And a somewhat exaggerated example is shown here, where the thermostat is very ill-placed and it has a bias against what the occupants of the room will usually experience if the toaster is on, for instance. There could be direct financial reasons, cost reasons due to which sensor precision can lead to the reduction in the quality of the data from the sensor itself. But we don't want to stop at just analyzing data quality against model accuracy. We want to try and also relate model accuracy against the performance of a closed loop model-based controller, because at the end of the day, people don't really care about mean square error as much as they care about dollars. So we understand that the performance should deteriorate as the model becomes poor, but if we can reveal the exact trend before you even make an investment to go this route, can that help you in lowering the cost and planning ahead? So my solution to this is what is called model IQ. It's a method in which you take information about what model you want to learn for the building, start with a preliminary data set that can be obtained from whatever data is already available, or if required, add some temporary sensors for a week or two to the building. It needs information about the estimation algorithm, which will identify the parameters of the model and what kind of model-based controller will you be using. And when you provided this information, it spits out the trade-offs between data quality, model accuracy, and control that I just mentioned. And the way it does that is using something called input uncertainty analysis, which has a very simple but effective idea that if you think about it, the accuracy of a gray box model depends upon primarily three factors. It depends upon the structure of the model itself and how well can it represent reality. It depends upon your performance of the estimation algorithm to identify the parameters from data. And lastly, it depends upon the quality of the input-output data itself. So the idea is that once you fix the model structure and the estimation algorithm, you can study or evaluate the effect of data quality on the accuracy of the model. So here's an intuition of the algorithm which can be used to do that. You begin with a data set, and each of these different data inputs is coming from a sensor data stream, and we want to evaluate that which sensors affect the accuracy of the model the most. So the first thing we do is we obtain our initial data and go through the estimation process to establish a nominal model or a baseline model for that particular zone or building. And then we will introduce artificial but meaningful perturbations in each of the data streams to create these copies of the original data, with the difference between them being that one of the data streams was artificially perturbed. We then repeat our estimation algorithm and obtain models. Again, the only difference between them being that some a data stream for a particular sensor was, we introduced some artificial bias into that sensor itself. And lastly, once we have these models, we compare them against the nominal model obtained from unperturbed or original data. And this process will help us to evaluate the influence of each of the sensor data streams on model accuracy. So we did this for the data sets from a real building. This building is located in the Navy Yard in Philadelphia, and the following analysis was done for one of the office spaces on the second floor of this building. So the first thing we do, like I said, is have to train a nominal model from the data which was available from the building itself. And the model is very accurately able to capture the evolution of the temperature of that zone. And this will serve as the nominal model against which we will compare models in which we are artificially introducing perturbations and biases in a random or a fixed manner. So let's look at what the results of that input uncertainty analysis looks like. You get these plots, and let me walk you through what's going on here. Every plot corresponds to a different sensor data stream, which is required for you to train the model. And there are two inferences of the plot over here. The first is that the model accuracy, which is plotted on the y-axis, changes inversely as you add more error to each of these data streams, which is plotted on the x-axis. And the second inference that we can draw is that all sensor data streams do not affect the accuracy of the model to the same extent, because you can just tell from the shape of the curve that some of them are highly sensitive. So it would be great if we can reduce all the information combined in this result of the analysis, which will allow us to compare different data streams and their importance in how they affect model accuracy, which is the goal that we want to establish, that trade-off. So that's exactly what we do. We define a model sensitivity coefficient in which is just the ratio of how much is the expected change in the accuracy of the model that you would see for every 1% of bias that you introduce in that particular data set. And we find out for this zone that some of the sensor values are extremely sensitive and affect the accuracy a whole lot more than some other measurements of outside temperature or ground temperature or some convective or radiative heat gains. But we don't want to stop here. We want to also continue this and figure out that is there a way we can calculate how the accuracy of the model now in turn will affect the performance of a closed loop controller. It turns out that analytically to analyze how MPC will come up with its optimal cost is very, very hard. Therefore, we use or rely on empirical analysis to reveal any underlying trends possible. So we set up a conventional model predictive control problem in which the objective of this optimization is to reduce the energy cost experienced due to changes in price of electricity while maintaining some degree of thermal comfort subject to the model that you want to evaluate and the constraints on the control input. So similar to the flavor of the uncertainty analysis, even in MPC, we first evaluate the performance of this model-based controller with the best model in which there was no artificial uncertainty introduced. And we can see that because the model has good predictive capability, it is able to pre-cool the building before the high price regions in pink begins. And that is the reason why it's able to result in a 14% cost reduction. But then we deliberately evaluate model predictive control by giving it a bad model in which the predictive accuracy is not that high compared to the baseline because of our artificial perturbations. And as a result of that, the savings that you can achieve from model predictive control reduce significantly. So if we do this for enough models of the varying accuracies, what we can reveal is the trade-off that we wanted to identify. That how does the expected savings that you achieve from your zone or building change as the model accuracy changes underneath it. And there is more than what meets the eye and what's going on in this plot. Just think about what it would take for you to improve the model accuracy in a certain region of this curve. It would take you to invest in sensors or improve the quality of data getting from that sensors. But the expected return in improving the accuracy of the model is negligible if you are in this part of this curve that we have revealed. But if you were to improve the same degree in another part of the curve, you can expect a better return on your investment in terms of the percent savings that you obtain. So these kinds of insights are usually hidden from operators who design or control engineers who design these model-based controllers for buildings. But such a simple empirical method can assist them in analyzing what is the bounds on the error of the models that they can expect to work with and what it would cost them in terms of sensor cost. So I did another experiment for the same office zone because we wanted to study the hypothesis that there could be bias in measurements of temperatures due to their location itself. This is one of the reasons for analyzing data quality versus model accuracy itself. So for this zone, we have the zone thermostat located on the south wall, but there are these different sensors which are uniformly distributed in the zone and they still measure the temperature. So we asked the question that is there a significant bias in the thermostat compared to the true temperature, which should be used to control or regulate the HVAC operation of the system. And you can think of this width of this gap band indicates whether there's a bias or not. And for that zone, what we were able to find out that was that even though there's a very small bias, just about 1% compared to the mean zone temperature, it can still affect the accuracy of the model that you learn, which will in turn affect the performance of your closed loop controller significantly because the zone temperature was one of the most sensitive attributes for this particular zone. So I continued this analysis further because I anticipated that once we have this capability of comparing the thermostat against the true mean temperature, why just compare one sensor with the mean? Why not try all possible subsets in the hope that can we reveal insights on improving sensor placement and density or making recommendations on whether you want to improve the model accuracy by 20% in this case. So which kind of sensors would you want to use and where would you want to place them? So for this, I use non-parametric statistical methods. Reason why I use them is because they don't make assumptions on normality of data that you want to compare against each other. And the way to interpret these plots is that the bias is indicated by the difference between the red line and the solid black line. So once we compute these biases for different possible subsets, Model IQ tool can also make recommendations on what would be the recommended location for placing a certain sensor given that how many sensors you require and what will be the bias that you can get out of them. So a non-intuitive result for this zone that was found out was that actually it's better for this zone that you have just 3 sensors measuring the zone temperature because this is a pretty big office space. And adding additional sensor does not necessarily guarantee that you would reduce the bias. So the contributions for this first part of the problem are the following, that I've come up with the ways in which I can quantify the uncertainty in the form in the sensor data in form of fixed biases or as a random uncertainty as well, and develop this input uncertainty analysis to quantify how data accuracy varies or influences the how data quality influences the accuracy of a model-based controller. I've come up with an empirical method of evaluating the accuracy versus the control performance trade-offs. And lastly, also included in this tool is a suite of non-parametrical statistical methods that can be used to make some decisions and analyze sensor placement and data conditions as well. So moving on to the second part or the second goal, which is can we make black box models more suitable and integrated better with a closed loop control? So just to refresh your memory, in DR, the idea was that you would be asked upon to curtail your energy consumption and you have to figure out a way to meet that reduction. And that is, in fact, the biggest problem that end users, like large-scale energy users of the electricity face, that how do you figure out which actions to take in order to get a sustained curtailment? Really, the name of the game for them is that how low can you go with your electricity consumption without it becoming very inconvenient for you or you're affecting your operations adversely. So just like the case for regular traditional control versus model-based control, even in demand response, primarily the majority of demand response approaches are rule-based. They rely on just historical experience of working with buildings and have a sequence of knob controls and switching of devices that can lead to some kind of curtailment. Or the other extreme is to go and model get white box and gray box models for these buildings in the hope of doing demand response. With data-driven demand response, what we really need is can we leverage the simplicity of data-driven methods or rule-based methods, but have the predictive capability of model-based methods. So here my solution is called DR Advisor or Demand Response Advisor. It's a tool that I have developed, and this tool is essentially acts as a recommender system for the building's facilities manager, and it works exactly as it's depicted here. So it's like an oscilloscope for a building, and it's looking at all possible data channels that your building generates. It uses that data, crunches it up, and makes insightful recommendations to the building's manager on what actions to take when he gets notified with a DR curtailment request. And the black box model that DR Advisor is based off is what is called regression trees. And the idea behind regression trees is the following, as described by the seminal algorithm for building trees, which is called CART. So really what we are trying to do is model the response, which is a power consumption, as some function of our predictors, or what we believe influences the power consumption to begin with. So for the case when m is equal to 2, let's consider this data space in which each of these data points represent some value of the response and how it varies with different values of my input features x1 and x2. So what CART does is it partitions the data space. So we can think of one of the partitions at x1 equal to t1, and then we can further partition one of these spaces at x2 equal to t2. And if we repeat this enough times, what we'll find is we'll end up with in these hyperrectangular partitions, and within each of these hyperrectangular cells, in order to make a prediction, because we have to make a predictive model, the prediction model we use in every cell is just the average of the data points which fall in that cell. So given some value of x1 and x2, I will just see which cell it lies in, and my predicted response will be the average value. So it's a very simple algorithm. But you can see how this set of rules, or the sequences of these splits, can also be represented in form of a tree, in which each of these rules correspond to the node of the tree, and down at the leaves, you have the predicted average response. So CART also specifies the questions that you might be thinking, that how do we figure out which variables to split on at which levels, and what is the value of T1, T2, and T3. So I won't go into very detail of how that is done, but those are really the questions of splitting criteria and variable selection specified in the CART algorithm. And it is obtained by solving a very simple optimization, which is very fast because you're only computing averages all the time and comparing the left average versus the right average. So as compared to linear regression, which assumes a global model, describes the entire data space, and has assumptions on linear additive modeling within the features themselves, in a regression tree, you don't actually use regression anywhere in the seminal algorithm. You are just dividing the data space into smaller cells and using the average predicted response there. But obviously, this can be extended and has been done over the last few years to include more complex models at the leaf other than just average itself. So for instance, M5 is one of the algorithms in which you use linear regression in the leaves, and then you can get as fancy as you can, and there's a lot of theory which I describe in my in the writing. One of the shortcomings of using simple algorithms like CART is, however, that they tend to overfit the data, but that is also resolved by resorting to ensemble methods, in which really the idea is that I'm going to grow a lot of trees and average their response rather than getting the prediction from a single one. So this is a traditional bias versus variance trade-off that we see all the time while building these models. So coming back to the context of buildings, the features that I train on, or the data that we need, can be classified as weather data, schedule data, or building data. So notice that weather data these days does not require you to have a weather station online. You can purchase weather data for virtually any location from third-party websites. Schedule data involves some proxy engineers, which we develop ourselves. So you don't need sensors to measure time of the day and day of the week. And then it involves any fixed schedules or set points, just like the chiller example I showed earlier. Some Excel spreadsheet set point that determines the operation of the mechanical or electrical equipment can also be thrown at the regression trees algorithms. And finally, we do require some data from the building automation system itself, because if you're trying to predict power consumption and hopefully want to control zone temperature set points or chilled water temperature set points, it's a good idea to measure them first. So once we have historical measurements of these different kinds of data sets, the idea in DR Advisor is that we are going to learn a family of regression trees rather than any single tree, with different trees responsible for a different demand response challenge that I'll briefly talk about. So there could be some tree which is solely dedicated to predicting the baseline power consumption, and some tree dedicated to figuring out the response or the actual control. One of the reasons why we also want to use regression trees is because they're very interpretable by design. And this is something which is required in the buildings domain, because building operators are very used to working with fixed logic and rules. So they cannot easily pass the decisions being made by complex models or being generated by something like a neural network, because there's no physical institution of the weights of such a model. So by design, DR advisor regression trees are very interpretable, and here's an example of that. So this is a tree trained on a year's worth of data with over 3.5 million data points. And it might look very intimidating, but at every node, there's a very simple, human readable, if this, then that kind of a statement that anybody can understand. You don't have to be an expert at anything to make sense of what's going on here. And essentially, when given a forecast of your predictors, you go through these questions very rapidly and converge at a particular leaf where you have some kind of a predictive response model. So the first thing we tried was to apply this suite of regression tree algorithms for the problem of baseline prediction, which simply stated means that can we predict what will be the power consumption of the building had it not participated in any curtailment request. It is very important to get this right, because any curtailment itself is measured with respect to the baseline, and it determines how much financial reward you get compared to how much you have curtailed. So I use a mix of both simulated data and real data from actual buildings in order to validate all of these approaches. And throughout the rest of the talk, when I talk about simulated test beds, I'm always referring to the Department of Energy's commercial reference building testbed, which is a model being simulated in Energy Plus, and it's a model of a 12-story large office space building. So when we try to do DR baseline prediction for this building, what we find is that our set of trees are able to predict extremely well the aggregate power consumption of the building during a DR event which occurred between 4 and 5 p.m. Sorry, between 5 and 6 p.m. In 2013, and our error is very low. We've also tried using these trees for making forecasts. So forecasting is very similar to baselining. And this forecast was made for building 101. This time, this is not just for a single zone, but for the entire building, trained on a year's worth of data from 2014 and tested on February 2015, which was really cold and then compared to last February. But still, the model is able to predict the power consumption really well. I've also used data sets from our own campus, and here are two examples of that, College Hall and the material science buildings. You might have to squint an eye to really look at which of the models get the accurate prediction compared to the ground truth. But what is of note here is that, again, the prediction accuracy is very, very acceptable, given that these buildings consume powers in hundreds of kilowatts. Then remember I told you that each building has to be uniquely modeled. Well, we tried it for different types of buildings: medical research facilities, office spaces where Ruben sits, and conventional lab spaces. And we find that, yes, the quality of data does affect how well we predict, but again, the predictions are quite well. And this has also motivated part of my research in just cleaning the data, but I'm not going to talk about that here.
So, quick question too, the prediction window, how far is it? 1 hour, a day ahead?
This is an hourly data that Penn generates, yes.
Because you need meteorological data. If you're predicting the whole month, it's not going to be very good.
No.
Okay.
Yeah. So I also compared the performance of the DR advisor approach against conventional data-driven or other data-driven methods. And the best way to do that was to evaluate the performance on benchmarking data released by ASHRAE. So ASHRAE is the American Society for Heating and Refrigeration Engineers, and they released a common data set in which they invited participants to try any data-driven model for 4 months of weather data. And the goal of the competition was that you don't only have to predict electricity, but in addition to that, you have to predict the chilled water and hot water consumption of the building as well. And then they evaluate the performance of your model on 2 months of data that you've never seen before. So when we apply DR advisor algorithms on this data set, what we find is that we outperform everybody who's participated in this competition except one team. So this is again a very good litmus test and a form of validation that these principles are sound and can be used to predict data sets for real buildings. So moving on from baseline prediction, can we now predict the actual response of the building? Because that's really what we want to figure out. That can we predict the actual response due to our inputs to the building? So in strategy evaluation, the idea is that because most of existing demand response is already rule-based, what if you have a demand response strategy which looks something like this? So you are changing some set points or turning off some devices, but there is no reason to believe that there could be just one such strategy. There could be different strategies, and then the question becomes, how do you choose a good strategy when the actual event occurs? So if your model can predict, in this case, the actual response of the building due to each of these strategies, then we can evaluate that and choose the best strategy at any given time. So going back to our representative building, here's an example of a fixed strategy which determines the zone temperature set point and chilled water set point for the duration of the event. And for my simulation, I considered the same two set point strategies, but the values of the set points were different for each. And then the question becomes, given now that we are changing these set points as the event is occurring, can we still predict the power consumption profile of the building? And the answer to that is yes. So the error is a little bit higher than for baseline prediction, but still very acceptable given that you are predicting on the order of megawatts. And the black line is the actual building energy consumption, electricity consumption profile. And you can see that some of the ensemble methods are somewhat off the prediction, but in general, we have a consensus among a lot of methods, and they are tracking the electricity consumption quite well. In fact, that's what we use to decipher that which models will we rely on for the actual prediction. The ones which are similar looking is the prediction we go for. So lastly, we come to strategy synthesis, in which the goal is still the same as evaluation, but in this case, we are not given any fixed rules or any fixed strategies. Our job is to figure out these strategies on the fly. And this is really the problem in which we want to leverage black box modeling and see whether we can do some kind of closed loop control with them. So in order to set this problem up, we first need to realize that when we were training this model, if our power consumption was the response, but our features were a set of both non-manipulated variables that we have no control over and set points that we can actually control or manipulate. And when we want to do synthesis, we want to figure out the values of these set points. So they are not provided to us as a part of the forecast. That is why we cannot rely on traditional cart-like algorithms in which we get a forecast for a mix of these variables and figure out which branch we will navigate to based on the forecast and make a prediction down at the bottom of the leaves, because we don't have the values of these. This is something we want to determine. And also this is a problem because when the tree structure is built, we cannot specify the order of appearance of different variables in the tree structure, because that would defeat the purpose of learning the tree from the model. And this order is being deciphered by solving this splitting criteria optimization. So therefore, if we don't have a forecast for the manipulated variables, we will not be able to navigate, because what if one of the layers had a control variable for which we don't have a value? We want to figure it out. So this is what motivated me to make a very simple idea and extend it, integrate it with regression trees, which allows us to solve this problem of figuring out control. And the idea is based on separation of variables, in which we learn the top tree only on manipulated, non-manipulated or disturbance variables, like temperature outside or time of day. And down at the leaves of the tree, we fit a regression model, which is only relating the response to the manipulated or the control variables. So what that allows us to do now is at every time step, we get a forecast of disturbances this time. So just xd1 to d3, d standing for disturbances. And those disturbances allow us to navigate the top part of the tree, and we will surely reach one of the leaves because we have a forecast corresponding to every feature which exists in this top part. And down at the down in the region which is chosen based on the forecast for the next time step, we use the linear model between the power consumption and our control variables, in order to figure out the values of these control variables by setting up some kind of a minimization of a function of a response. So I want to lower the power consumption subject to the model which is valid for that next time step, which is being given to me by this specially built tree, and subject to the constraints on the control input specified by the user. So when we use the synthesis algorithm for our building, what we find is it leads to a very good curtailed response for the duration of the event, and which is a very good sign. And if we look at what it synthesizes, so in this case, we are synthesizing 3 different set points rather than just 2. And although it looks like a flat line, there are some fluctuations in the solution of the synthesis algorithm. And if we zoom in to how the model selection at every time step behaves, you can see that at every time step, based on the forecast of just the disturbance inputs, the model is able to determine which leaf to go to and use that particular linear model to figure out the set points for sustaining the curtailment. So we also computed what is the expected revenue that you could obtain if you were to implement this on a 12-story large office building. So I used the actual utility tariff structure from Con Edison, which is a utility based in Chicago. And based on their rate structures, and assuming that we have about 5 events per month for the length of an entire summer, what we see is that you can expect to save about 40K for just one commercial building over one summer. So this 40K is as a result of no additional expense of hiring domain experts or building those gray box or white box models. We are just relying on very, very richly available data sets, which are weather data, schedule data, and are able to do sustained curtailments using that. So the contributions for this other half, the second problem were that we have demonstrated that the benefit of using regression trees for building modeling and applications to demand response, eliminating the last mile challenge of how to figure out how you curtail, and also getting away with some of the cost and time efforts required to build these buildings. I've also shown a method on which you can use DR Advisor like tools to do strategy evaluation and choose the best predetermined strategy during the event out of existing strategies. And lastly, I presented a model-based control with regression tree algorithm that can be used for closing the loop with black box modeling. So DR Advisor has also been developed into an actual tool, which is available at this URL. And then this tool allows you to upload your data sets from the building, specify their duration and the sampling time. And we train all these models that are described. You can even choose, if you know what you're doing, to tune some of the hyperparameters of these models and go all the way to baseline prediction, evaluation, and synthesis. So my hope is that DR Advisor is going to run at this data intelligence layer as a service, pulling all possible data from the buildings or a campus, and it will have 2 different types of clients. So it'll obviously have end users as these clients, which will use DR Advisor's insights to figure out how to do demand response. But we can also think of the curtailment service providers or the aggregators, which can use DR Advisor to figure out better ways of sending the dispatch. So I would only request you how much to curtail if I know what is your capacity right now to curtail given all these data sets. So finally, to conclude with the summaries, I presented a challenging problem which involved learning accurate models for doing model-based design for these large, messy cyber-physical energy systems. We need these models because we want to have some demand flexibility in the way we consume electricity and protect ourselves from the volatility in electricity prices and be able to do demand response. I have developed methods which use both empirical techniques and some analytical techniques to do cost-benefit analysis of adding additional sensors to a building in order to do traditional gray box methods. But I believe the primary contribution is also that I've come up with a data-driven and control-oriented modeling for these energy systems, applied them to demand response, and established a method in which we can use these black box models but still be able to do high-level control with them. So So far, as first half of my research was pretty much spent working with gray box models, and my focus was more on the control side and how can we come up with peak power reduction algorithms which compete with MPC but are much simpler. I had also worked on tools which can hook up to white box models and make it easier for us to use them, and that tool is called MLE Plus. But the research I presented today has also been published at different venues of cyber physical systems, automation, and buildings, and some of it is still under review at buildings conferences and energy journals. So my ongoing plan and ongoing work is the following. I think there are three big extensions I can add or make to the work which I presented today. The first thing to note here is that uh, the model-based control with regression tree algorithm that I showed did not explicitly account for thermal comfort, right? So we are curtailing, but we are not accounting for what's the effect of that curtailment on the thermal comfort, and that is very, very important, which is why I think it can be extended to account for thermal comfort explicitly as a part of the objective function that you solve at every leaf, or also as a part of the model at the leaf itself. And once we do that, my aim is to also use and address that supply side problem of figuring out the optimal demand response dispatch for aggregators like an NRNOC. Another extension I want to make is that so far I've used this framework for just demand response, but it turns out that uh, people also want to know more about, because gray box models have the also have the capability to provide insights on the building operation. So I feel that even these regression trees can provide that interpretability and provide you analytics on how your building behaves by mining through that tree once you have learned it. So the idea here is that I have built a framework in which you can query the models that I have learned, and they will be able to reveal answers to open-ended questions like under what conditions does my building consume so and so kilowatts, and what's the set point during that time, or what time of day is it during that time. There's another goal behind doing analytics with regression trees, because as you grow ensemble trees, you do lose some interpretability of the rule-based at every different node of the tree. But I think this framework of extending it by adding some analytics capability will restore the interpretability of even ensemble methods. And lastly, the model that we learn for the building in order to do our DR is not a dynamical model. It's an input-output model. So I can predict the power consumption based on the forecast of disturbances. I do feel, however, that the similar idea can be extended for dynamical modeling or time series modeling, something like predicting the temperature evolution of a room. So here my idea is to, instead of doing auto-regression, you can do auto-regressive trees and still be able to do something like receding horizon control and not just single time step look ahead control. So I want to thank my committee for being here, and also for providing me feedback directly over the years and indirectly through your work that has definitely shaped my own thinking about this problem. Over my PhD, I was fortunate enough to work at different organizations, both inside and outside of Penn. So I pretty much want to thank everybody I've interacted with over the last 6 years, including all folks at MLab and Precise. And definitely a special thanks to a few of my colleagues without whose efforts and help, it would have been really, really difficult for me to present all the research that I've presented today. So I'll stop here. It was just in time. And if you have any questions, I'll be happily able to answer them.